All right, let's get started. Today, we're doing something a little different. Instead of looking up at the stars, we're going to take an incredible journey down, deep into the heart of our own planet to figure out what it's really made of.
I mean, it's pretty wild, isn't it? We've got maps of galaxies that are millions of light years away, but what about the ground we're standing on right now? What kind of secrets are hiding just a few thousand kilometers right under our feet? It's this whole other world we can't see, but, it shapes literally everything about our lives.
So, you ready? Let's dive in and start peeling back the layers of our planet.
Okay, so our first stop on this journey is the layer we know best, or at least we think we do. It's the Earth's crust. Now, the best way to think about it is like the skin of an apple. It's super thin, kind of brittle, but absolutely crucial, even though it's just a tiny, tiny fraction of the whole planet. And when you look at the scale of it, it's just mind-blowing. The crust is the thinnest outermost layer, and get this, it makes up only 1% of the Earth's total mass. 1%. And yet every single thing, every city, every ocean, every mountain, all of life as we know it, it all exists on this incredibly fragile little shell.
But here's the thing, not all crust is created equal. It's actually split into two main types, and we've got some handy nicknames here to help remember them. First, there's Sial, which makes up the continents. That's for silica and aluminum. Then you've got Sima, which forms the ocean floors. It's heavier, denser, and rich in silica and magnesium. So the key thing to remember here is that the lighter continental crust, the Sial, is basically floating on top of that denser oceanic crust, the Sima.
All right, we've made it to the bottom of the crust, and it's not some gradual, fuzzy change. Nope, it's a really sharp boundary where the rocks suddenly change completely. It's called the Moho-Ravishik discontinuity. Yeah, thankfully everyone just calls it the Moho for short. So think of the Moho as the floor. To go any deeper, we've got to go right through it.
And just like that, we're through the Moho. We are now officially descending into the mantle, the massive middle layer of our planet.
And when I say massive, I am not kidding. Just look at this number, 84%. That's how much of the Earth's total volume the mantle takes up. It is, by a huge margin, the biggest layer of our planet. Seriously, the crust we were just in, it's just a thin film floating on top of this enormous ocean of rock.
So what's it like down here? Well, for starters, it's about 2,900 kilometers thick, and it's made of this hot, dense, kind of semi-molten rock. Now, a really important part of the upper mantle is this special layer called the asthenosphere. It's a bit weaker, and it flows, kind of like super thick hot plastic. And this is so important because the rigid plates of the crust are floating and moving around on this gooey layer. And the temperatures? Oh, they can get up to 3,700 degrees Celsius down here.
Okay, buckle up for the final leg of our descent. We are going deep, pushing through thousands of kilometers of superpressurized rock to get to our final destination, the core. This is it, the superheated engine at the very heart of our world.
We made it. We're at the very center of the Earth. The core is the innermost and by far the densest part of the planet. It's mostly made of two metals, nickel, that's Ni, and iron, Fe. And that's where it gets its cool scientific nickname, knife. Pretty easy way to remember what it's made of, right?
Now, the core isn't just one giant solid ball. It's actually got two very different parts. First, you have the outer core, which is this swirling, churning layer of liquid metal about 2,200 kilometers thick. But then you go deeper and you hit the inner core. Now, here's the crazy part. Even though it's even hotter here, the inner core is completely solid. Why? Because the pressure from the weight of the entire planet pushing down on it is so immense that it literally forces the atoms to lock together into a solid.
And speaking of hot, just how hot are we talking? Well, the inner core is estimated to be around 6,000 degrees Celsius. Let me put that in perspective for you. That is as hot as the surface of the sun. We are literally inside the furnace of our planet right now.
So you remember the Moho separating the crust and the mantle? Well, there's another major boundary down here. The line that separates the rocky mantle from the metallic core is called the Gutenberg discontinuity, and that marks the final major transition zone on our journey to the center. Okay, wow, we have traveled all the way from the surface right down to the center. So let's do a quick recap, a little cheat sheet. We've got the super thin crust, which is our home. Below that, the massive mantle, making up a whopping 84% of the Earth's volume. And finally, the super dense core, nicknamed knife, with its liquid outer part and solid inner part. This little table here is a perfect way to lock in the key facts from our trip.
So, that was our journey. But this probably brings up a pretty big question, right? How on earth do we know any of this? I mean, we've never drilled to the mantle, let alone the core. It seems totally impossible. So, what's the secret? How do you see inside a planet?
Well, the answer isn't about digging, it's about listening. You see, all of our knowledge about what's inside the Earth comes from studying seismic waves, those incredibly powerful shock waves that come from earthquakes. You can think of them like a planetary-scale ultrasound, giving scientists a picture of what the Earth's interior looks like.
And this is where the geological detective work gets really brilliant. So earthquakes release two main types of waves, P waves and S waves. P waves are tough. They can travel through pretty much anything, solids and liquids. But S waves, they're different. They get stopped cold by liquids. They just can't pass through. So when scientists were tracking these waves zipping through the planet, they noticed something amazing. The S waves completely vanished when they hit the core's boundary. That was the smoking gun, the absolute proof that the outer core had to be liquid. I mean, how cool is that? It's just ingenious.
Okay, so we know the structure, and we know how we know it. But so what? Why does any of this deep, internal geology stuff matter to us, living our lives up here on the surface? Let's connect all the dots.
You see, the core isn't just some hot, dense ball sitting there. It's a dynamic, living engine. That churning liquid outer core of iron acts like a giant dynamo, and it's what generates Earth's magnetic field. And that field is basically an invisible shield, protecting all life on Earth from deadly radiation from the sun. Plus, the core's intense heat is what drives movement in the mantle, which in turn moves the tectonic plates. That means everything from earthquakes and volcanoes to the very shape of our continents. It's all a direct result of that engine running deep, deep inside our planet.
And that brings us to one last pretty profound thought. We've seen just how absolutely vital this internal heat engine is for everything, from our atmosphere to the ground beneath our feet. So I'll leave you with this question to think about. If the Earth's core ever cooled down completely, what do you think would actually happen to life on the surface?